Hi, everybody. Oh my gosh, it's so exciting. I'm back after a couple weeks. I think I'm going to do this every other week, providing people care and are watching. Welcome to Saturn. My name is, as always, is Dr. Kevin Hainline. I'm an astronomer at the University of Arizona, and I thought that while we're all in quarantine, I'd use some time to help us explore the universe using Space Engine, which is what I'm using behind me. And as I wrote on the pre-stream image there, this is like a somewhat live but simulated image of what it would look like right now if we were kind of floating over the surface of Saturn, looking at the sun through Saturn's rings there. So I'm an astronomer who studies distant galaxies and black holes. Last time we talked about how stars live and die, and this time I thought we'd look at our solar system. There's a whole bunch of stuff there, and we could devote, I've taught an entire class in the solar system. But I think that what I'd rather do right now is give just broad overview and some cool shots of the solar system and the planets. And if you have any questions, you should definitely just let me know. So, in the chat. So I'm monitoring the chat right here, and if you have questions, please ask, and hopefully I can answer them. And they don't have to be about what we're doing. They could just be about anything astronomy, or just about me. I'm doing pretty well. The cat knocked something over today, which knocked over a bunch of water. So the cat's not in my good graces at the moment. But otherwise, things are pretty good. So let's zoom out a little bit here. So I'm gonna zoom away from Saturn. So here, if I increase my speed a little bit, we can see this beautiful planet. And you can see that I was in the shadow of the rings here. These are the shadows of the rings. And we'll come back to Saturn in a little bit. But I wanted to start here because most people, it's their favorite. You can see over here all these bright fuzzy blobs. Those are some of the moons, and we'll talk about that a little bit as well. But let's zoom out really far from Saturn. Just flying around. Here's the sun right there. You can see Saturn as it flies off. And let's start with the sun. So that's what we talked about last time. So if you remember last time, hi. Oh, thank you. This is my Tucson hat. Hi, Cat. Last time we talked about stars, and we talked about stars insofar as we talked about how they lived and died. And as I mentioned, our sun is a star that is in the middle of the prime of its life. It's 4.5 billion years old, like the planets. It's taking a simple element called hydrogen and turning it into helium in its core, which is like this process that will define most of its life. It's about 5,000 degrees Kelvin on its surface, so incredibly, incredibly, incredibly hot. You can see the granules we talked about last time and the sunspots. And just to give you an idea how big the sun is, compared with the planets, the sun is the reason that we have a solar system at all. So, the solar system, the word solar means sun, so it's the sun system. So it's a pretty important star for us, but it's not as big as some of the other stars. Last time we looked at Betelgeuse, which is enormous. But let's go over to this mode here, where we can see all the planets in the solar system to scale. So you can see how big the sun is, right? And maybe you're going, well, Jupiter's pretty big compared. But like Earth is right here, and if I zoom in on Earth, you can see Earth right there. Let's get them in the same thing. So you can see Earth over here on the right, and then the sun, right? So about 1 million Earths could fit inside the sun. It's enormous. Now this is not how the planets are like actually distant from each other, and I can show you that in a second. But just wanted to let you know, this is the sun system, and it's called the sun system, or the solar system, because it's mostly the sun. Most of the mass, most of what went into making the solar system is in the sun. It's the big thing. We are just the leftover little bits that went into making these planets, right? And so there are 8 main planets. We're going to talk about them: Mercury, Venus, Earth, and Mars. There's a bunch of asteroids like Ceres here. Then there are four gas giant planets. So these are the inner planets are terrestrial, and these are gas giant planets. And then outside of that is a bunch of other objects, including the dwarf planets, which I actually just turned off. So you can see the dwarf planets down here, and we'll talk about them, including Pluto, Haumea, Makemake, Eris, and we'll talk about those as well. This is their order, and the way that I remember this, and this is really silly, is MVEM, right? Is the way that is historically is my very elegant mother just served. I turned off. Just served us nachos. Let's just do system architecture. Whoa, yeah, there we go. Let's close this window here. Oops. I'm closing things incorrectly. Okay. It's my very elegant mother just served us nachos. My Mercury, Venus, Earth, Mars just served us nachos. When I was a kid, Pluto was considered a planet, so instead of nachos, it was 9 pizzas, which is, I think, too many pizzas. So for right now, my very elegant mother just served us nachos. And you know what? My very elegant mother sometimes serves us nachos. If you're watching, Mother, you're very elegant. Thank you for serving me nachos in the past. It's helped me remember the planets. So what we're going to do is we're going to go through the planets starting from the inner one on out. I'm going to talk a little bit about their characteristics and stuff. But you can see in terms of size, this is them arranged by size. Sun all the way down to the dwarfs. All the way down here, you can see the way down here is Galatia. I think Galatia is a moon. We can arrange them by mass, which is very similar, but notice that Neptune has more mass than Uranus, just by 17 but Uranus is bigger, right? And that's because Uranus is less dense than Neptune, which is kind of neat. Never enough pizza. Yeah, exactly, right? And if you do density, you can see that over here, we have gas giants, and then we have, they're oriented in a really interesting way in that, the most dense one is down here, 5.531, 5.41. This is very dense, but then you have even denser rocks, Despina, Thalassa, Naiad, Cressida, very dense. And then the sun, and then is, halfway through. In fact, there are some planets, like some moons, that are a little bit less dense, whoops. And if we arrange them by temperature, you can see that the sun is really, really, really hot. But notice, Mercury is not the hottest. In fact, Venus is the hottest. We'll talk about that in a second. But this is pretty cool, right? So, we've got all this, we've got all this really interesting facts here. But let's go to the planets. We don't want to see this. This isn't that fun. So, I'm going to bring up my factoid sheet. Dwarf moon Galatia is a Neptune moon, for those of you who are wondering. So I think that if I had 9 pizzas, Cat, I would probably barf. So let's start with Mercury. Mercury is the closest planet to the sun. Let's center it. Let's go there. What I'm going to do is I'm going to show you the external, and then we'll try and land on the surface and take a look at. And if I'm not loud enough or anything, you should just let me know. Hopefully you can hear me pretty well. There's no music playing while I do this. I could probably play music, but that'd be, I think, distracting for my wonderful voice. It's taking us a second, and bam, here we are, Mercury. Okay, and so if we want to look where the sun is, we look back where we came from. There's Mercury. You can see that one side is here lit, and that's because it's the side pointing towards the sun there. Right, here's the terminator, the region where the sun stops. So where sunset would be right now, or sunrise would be. Mercury looks like, as you probably just noticed, the moon. That's because both of them don't have atmospheres. In fact, Mercury, I think, is a little bit smaller than our Earth's moon. It's actually a little bit larger, just a little bit larger than our Earth's moon, and it has all of these craters here. Craters come from little rocks flying through space that crash on the surface very, very hard and make these, boom, and you get this kind of like rupture and sends material off, which creates this little mountain. We have these on the planet. There's one in Arizona, a meteor crater like this. But because we have an atmosphere, it protects us generally from quite a few of the big craters, which is, thank goodness. So if we stand here, we can go and look back up. Let's land right here. Are you ready? So now we're on the surface of Mercury. We can look up at the sun, and let's put on some sunshades. In the sky, Mercury, the sun is maybe 3 times as big as it would be for us on the Earth. On the Earth, the sun is a certain size. We can't really see it, but because of Mercury's being so close to the sun, the sun appears bigger, as you would expect. When's the next episode of the Stars Connect us? 13J? Hopefully in the next couple weeks. I have to do a talk for a group next week, and then after that I've got the next episode in written, and I need to actually record it. So hopefully next week. And I appreciate you asking, because I need to do that, and I didn't even think people watched, but I appreciate that. But it would feel like being on the moon, pretty much. Whoops. Don't know where that has gone. Well, there we go. Don't know why I have lost control of my... there we go. I click track object. I feel like being on the moon, except way, way, way hot. Here's a couple of cool facts that I like about Mercury. So, first off, if we go over to the Terminator here, you can get a really cool look at the sun. Like sunrise or sunset. Mercury, one day on Mercury is like one year is 88 days. 88 days to go around the sun, right? And its rotation period is like 1,400 hours, which is about 58 days, okay? So what that means is that it takes 58 days to rotate around, but yet to go a full year for Mercury is 88 days. And these I'm talking about Earth days, which is kind of a ridiculous thing to think about. I really like when you get really... There we go. Oh, right there. You can see the sunrise. Mercury has a really interesting orbit. Whoops. I turned on the constellations there for a second. It's got a really interesting orbit in that it is like an egg shape. It's only barely an egg shape, though. So if I turn the orbits on, and then we zoom out quite a bit, and look over here, you can see that Mercury's orbit, it looks fairly circular, I recognize. But it's actually kind of weird where in that one side it gets a little closer and then farther away, and it's actually a little bit more elongated. The other planets have way more circular orbits, but Mercury's is not, which I think is pretty interesting. 88 days for it to go around. 88 days. Not so bad, right? You know, we potentially might be in quarantine longer than that. So one Mercury year will be our quarantine time. So let's look at Venus next while I'm doing this. So we'll go back over here and Venus, because Mercury is fairly moon-like. Venus, the second planet, is not at all moon-like. Venus is about the size of our Earth. It's maybe a tiny, tiny bit smaller. And Venus, it's mostly noticeable from space in that when we take pictures, in that it's just not super interesting to look at. Like, there's not much that you can see. And because you're not looking at the surface, this isn't the surface of Venus. What you're seeing here is you're seeing the tops of a very, very thick layer of clouds. These clouds are mostly composed of something we know here on Earth. It's carbon dioxide. You breathe it out. American industry and world industry pumps it into the atmosphere. And the thing is that most of the atmosphere of Venus is carbon dioxide. And carbon dioxide acts like a blanket, and that blanket essentially traps and retains all this heat, which means that Venus is the hottest planet in the solar system, even though the sun is much farther than Mercury. And so we've sent spacecraft to Venus, landed there, many of them. And the problem is that it's so insanely hot that when they land there, they can't survive very long. So if we just so I'm going to slow down and we're going to just crawl our way in the atmosphere here as we go. So the atmospheric pressure is now rising. You can see that down here I have the atmospheric pressure of where I am currently and the temperature we have, negative 152 degrees Fahrenheit. But as we get into the surface, you can see now we're in the so now we're at 1 atmosphere of pressure. So this is 1 atmosphere of pressure. If you were floating here over the surface of Venus, it would feel like standing here on the Earth, except it'd be, as you can see in the parentheses, 0.4 degrees Fahrenheit. So almost 0. So you could, in fact, stand right here and wear like a parka or something like that. It'd be very, 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 very cold, but you could do it. And in fact, you could actually go down a little bit farther to something like, like here. This is like 68 degrees Fahrenheit, right? So a nice day. It's only 1.75 atmospheres, so you'd feel a little bit heavier. The atmosphere would push down a little heavier, but you'd feel pretty, it wouldn't be so bad. The problem is there'd be a lot of carbon dioxide, so not the greatest. But you could stand here, and if you had like some sort of breathing apparatus, you wouldn't die of the atmospheric pressure or the temperature. But as we continue, notice here how far away we are. Like, we're still, at an altitude of 25 miles above the surface, right? So we're still 25 miles into the atmosphere. So if we keep going down, Notice the atmosphere goes up without 5 atmospheres of pressure, and the temperature has risen to 200 degrees Fahrenheit. So it's getting rapidly hotter. And the thing is that we're up here at this temperature where it's like 60, 70, 80, where it's almost 2 atmospheres. The winds that are here are like incredibly fast. This atmosphere has these incredibly turbulent winds. And so it wouldn't be the most fun place, but you could potentially imagine visiting there. But as we get closer and closer, notice we're 400 degrees Fahrenheit, 13 atmospheres of pressure. And as we finally land on the surface here, boom, rocky surface, similar to the Earth's surface in its composition, rocky, gray, looks like a hazy day here on the Earth. There's the sun right there. Notice it's 880 degrees Fahrenheit with an atmospheric pressure of 72 times pushing down on you. You know how you never feel what the air pushes down on you generally because you're pretty strong compared to it? You would feel 72 atmospheres of pressure. It would feel like 72 times the amount of pressure that's pushing down on you in the air would be pushing down on you. Incredibly, incredibly high pressure. Mostly carbon dioxide, as you can see, and nitrogen. The gravity is about Earth's gravity. You could stand here. A day is about 8 years, which is kind of crazy because it just slowly rotates. And it rotates, though, around the sun in 243 days, right? So it's a very slow rotation. And it also, Venus rotates backwards, which is very, very weird. But you can see as we fly over the surface that it has mountains. The largest mountain on Venus is a mountain that's about the size of Mount Everest. We think that there was a lot of volcanic activity on Venus in the past. But for right now, when we've sent robots there, they've landed and mostly just discovered that it just has rocks on the surface. And, but with acid rain, sulfuric acid in the atmosphere, it's pretty intense. Not a fun place to visit. If someone says, hey, let's go visit Venus, you say, can I stay in a specific spot in the atmosphere? And they say, sure, but I'd like to go to the surface. And you go, no, that's dangerous. But you can look here in this surface. You can see things that in the simulation where they've tried to simulate, like tectonic and former volcanic activity. Pretty neat. Venus, hottest planet, right? Kind of a warning about, like here, you may think, okay, well, is it hot in the evening as well? If we go land on the evening side, so let's go land here. All right, so I think that we are now, lost. Whoops. Let's rise up again. I think I've just, whoa. Let's find, oh, there's Venus again. All right, okay, so here's Venus. Let's land right on the surface in the evening. It's hard to see. I can make that a little easier to see. All right, so very, very dark at the moment. Not really much you can see. But notice it's 838 degrees Fahrenheit, even at night. It's because the atmosphere acts to trap that heat in like a blanket. It's like an incredibly thick atmospheric blanket. So don't hang out on Venus. Just don't. So we rise up again out of the atmosphere. All right, let's go find the third planet out. Earth. Earth is a planet you're probably pretty familiar with. I like it quite a bit. Here you can see floating over it, we can see California, Baja California, Mexico. You can see that currently the East Coast is dark, and they've simulated all the lights on in the various cities. Although I think right now the cities probably aren't as bright because people aren't out as often, and so it's probably a little bit, the simulation doesn't take into account that we're all sheltering in place generally. But the Earth I won't talk too much about. 1 year is 1 year. 1 day is 24 hours. It's got water that's liquid because it's close enough to the sun that the water is not frozen, but far enough away that it's not like boiled off. It's like a really perfect place to hang out. If people say, I want to hang out on the Earth, you say yes. If they say maybe up in the higher atmosphere, you go, that's a little dangerous, but sure, as long as we take precautions. It's the best planet for life in that it is the only planet we know of that has life currently. But pretty nice. I like it quite a bit. It's got an abundance of life. It's the only planet we know that we want to live on, that we can potentially think about living on. I would not recommend visiting or thinking about living on other planets. So there's New Zealand here. It's like, what island? This looks like New Zealand, right? Here's New Zealand. Anyway, we're not here to look at the Earth. Earth is cool. We want to keep moving on. So for right now, let's go. Here's actually something interesting about the Earth. So if we look at the Earth, where the North Pole is up here, right? So you can see that the North Pole is right. Oops, I'm going real fast. Notice that this line here is actually like, it's not like this is north, but the line is like diagonal across. Like you'd think that like, oh, shouldn't this line be going from north to south, right? Like shouldn't, well, actually right now we're entering the summer. We just had, the spring, the vernal equinox. We're entering the summer. And what happens is the earth is tilted on its axis. So its axis, what points up and down, and we can put on, I guess this may or may not help. Probably not. The axis that goes through the earth, like North Pole and South Pole, that is actually tilted right now a little bit toward the sun. So if we're up at the North Pole right up here, we're at the North Pole, we're going to see the sun all day. And so people who live in the Northern Hemisphere during the summer, like, if you live way up here in northern Russia, there's going to be periods of time where the farthest that the sun goes is just like really low on the horizon. It's just like it never sets. And then in the winter, you get 24 hours of darkness because now, just like in the Southern Hemisphere down here, so if you look down here at like where Antarctica is, this part of Antarctica is just going to see darkness all the time, right? Like the way that they have the sun so low, they just don't see it because the earth is tilted towards or away from it. So like if we landed right down here, whoop, oh gosh. Where's the sun? Let me turn off these lines. Where's the sun? If I go and do home and do home again and center the sun is below the surface right here, right? And if I were to like rapidly change time, notice all the stars moving, right? What time is it? Well, it's, midnight. Up. And so the sun is rising. There it is. It's just going to barely graze the horizon. So this must not have been far enough south, here on the Antarctica. Or maybe it's just because it's not the summer yet. But this is as far north. That's noon right now in Antarctica, where I'm standing. Bye! And there you go. There's the sunset. That's it. That's what the sun does. Pretty cool. So let's set the normal time speed and set it to now. Boom. And let's fly up into the sky again. You can see the southern, the Aurora Australis, which is the southern lights. And let's move on. So, we talked about Earth. Let's keep popping out to the solar system browser, and we'll click on Mars, and we'll center it, and go there. So, hope everyone's doing all right. We're flying now towards Mars. It takes a little bit. Mars is not as big as the Earth. Mars is actually a lot smaller than the Earth. So when we get there, I'll show you. There's Mars. If we look back at our solar system browser, nope, that's not the one I wanted. This one. You can see how big they are compared with each other, right? Venus and Earth, very similar. Mercury, bigger than the Moon. Mars, kind of runty compared with the Earth. Not, like maybe, 2/3 the size, a little over half the size. And so let's go back out. Here's Mars. And to give you an idea, I was talking about this on another stream, but this is called the Valles Marineris we're looking at right here. It's this big canyon across the surface of Mars. And if you put Los Angeles over here, New York would be over here. It's this incredible canyon. So people talk about Mars as like, oh, can we go live on Mars? Can we go live on Mars? Well, we probably wouldn't want to. So let's land right here. Whoop. All right, so now we've landed on Mars. Here we are on Mars. Wow, look, that was easy. Notice if we go back over here what our temperature is. Negative 64 degrees Fahrenheit. It's the middle of the day on Mars here. Negative 64 degrees, though. Huh. What's our atmospheric pressure? Hardly anything. Almost zero. Oh, great. Thanks, DSH. I think that Phobos is my favorite. We'll talk about those in a second. DSH is asking about the... and I know who DSH is, but I try to be nice on this and not reveal identities. If we go fly over towards this canyon here, you can see that it has not loaded in the canyon at the moment. Mars looks very smooth, buttery smooth here. But notice Mars is not particularly hot. It's incredibly cold. Notice it says cool arid subterra. Not because Mars is a really cool arid subterra. That's real cool. Cool arid subterra. Because it's actually very, very cold. It is not a place that we can imagine living because for the time being, because right now we'd have to really probably live inside all the time where we can warm it up. There's not a lot of liquid water that we can get out, and what liquid water we think is under the surface is probably not drinkable at the moment. It's a place that I think is incredibly interesting to think about. The problem is, look at us, we weren't even in the actual main canyon. Here's the main canyon. The Valles Marineris here. The thing is that it's just... It looks warm because we think of it as warm because it's Mars and it's red, right? But look, negative 64 degrees Fahrenheit. Not great. Here, now we are here inside of the Valles Marineris, this canyon. This canyon, landing here, looking around, this is like an incredibly distant, walls on either side. Like our own Grand Canyon is much, much, much smaller than this, right? Much, much, much smaller. The largest mountain in the solar system is right up here. Wait, let's make sure that I know which one it is. There it is. This is the largest mountain in the solar system. This whole mountain here, whoops. Gosh, I need to learn how to do this better. Whoa, whoa, whoa. I've done the thing again. There it is. This mountain right here is known as Olympus Mons. And just to give you a size, this is the size of Arizona, the state of Arizona. You could put all of Rhode Island into the crater up here. It's a former volcano that is the tallest mountain. So let's land in the crater, and I'll show you exactly. So we'll land. I'm gonna slow down. We'll land right here in the crater. I assume that Dr. Manhattan would be right in here, but I couldn't show him on stream because I'm trying to make sure this stream is PG. Notice it says right up here how high we are. Where's our? I guess it doesn't have our altitude. It's 11 miles. So it's 11 miles off of the surface, the sea level. So like we are only 4 feet off, but 11 miles off of the surface from sea level. Well, there's no real sea level here. So imagine an 11-mile high mountain. That's the size of Arizona. One of my favorite facts about this, and I had my students in my class, calculate this, is that because of the gradual slope of this, you could wheelchair up this. It'd be like not a very hard climb. Olympus Mons, I thought was maybe the coolest thing when I was a little kid. Mars has polar caps. You can see one here. And the polar caps have quite a bit of carbon dioxide ice, which we call dry ice. And under them is probably liquid ice. So you could imagine maybe living here and like mining the ice out here if you could figure out a way to somehow turn it into, filter it so that we could drink it. The thing is that it's, again, very, very, very cold. I think that when people talk about living on Mars, we'll just go live on Mars. That's the place to do it. We don't think, that's way worse than trying to live in Antarctica. Or the most frigid parts of Siberia. So, DSH asked about which is better, Phobos or Deimos. So, Phobos and Deimos are Mars' 2 adorable little moons. And I use moon liberally here. They're not even listed as a moon here. They're just listed as a cool asteroid. Here we are, getting close. Mars is very close to what's called the asteroid belt. We'll talk about that in a second. And so it's captured a couple asteroids. And here's Phobos. You're wondering, why is it shaped like this? Well, remember, it's not like our moon. It's much, much, much smaller. How much smaller? I'll show you. Shoop, shoop, shoop. Here's the moon. Here's Phobos. Haven't gotten to the point where I can show it off. There's Phobos. Now I'm zooming out. There's the moon. Much, much smaller. Just a captured asteroid, but we can do this. We can go and, oh man, it's let's land on the surface and point ourselves right at Mars. Whoa, now we're inside of Phobos. All right, cool. Guess we can't. Can we land on Phobos? I want to land on Phobos. I've never had it where it's zoomed through. All right, so let's land on Phobos. Look up at Mars. This is what it would look like from the surface of Phobos to have Mars there. And we can do this. Here we go. We get a wonderful Mars rise, day rise here. Pretty cool, huh? This is what it would look like. Your day here on Phobos. Hanging out, having a picnic on Phobos. Look up. Boom. See all of Mars? I mean, I'm making time go by 100 times as fast, but pretty neat. So, now the question is, let's go back to now. Where is Deimos? There's Deimos. Are you ready to go there? Boom, and we're off. I'll go faster. So here's Deimos. Also potato-shaped, like a Yukon Gold with a divot here. All right, so DSH, now that you've seen both, which one's better, Phobos or Deimos? I think I'm a Phobosman myself. Where's Mars? If we land on the surface here, I don't know why I can't see Mars. Am I just like totally missing it? Is it on the other side of this? Why am I not seeing Mars? Weird. Oh, I did it again. We went through the dang moon. Cool asteroid. All right, so now if I go and find Mars, if I turn on my solar system chart, nope, that's not what I wanted to do. I wanted to turn on this and center it. Oh, it's farther away. Mars isn't nearly as cool. That's why. But from here you can see, whoops, why do I keep clicking on that? That is not what I want to do. You can see Phobos over here. All right, so Mars, Phobos is sort of like, I think we're waiting for DSH to answer that. Notice also, you can see the Pleiades here. You can see the V of Taurus the Bull. Here, let's zoom off into space. And I'll show you something neat. Oops. Notice, this is the V of Taurus the Bull. Here is Orion. If I turn on my constellations, you can still see the constellations. You're saying, but we're floating in space away from another planet. How could that even be? And that's because the stars are so far away that at nearly every spot in our solar system, everything looks almost exactly the same, right? It's like a horizon of stars that are way, way, way far away and hardly move unless you get it. All right. A half-turn head. Oh, a little sassy look, a little Phobos sassy look. Why are you doing that? Let's go investigate this sassy look. Half-turn head. Yeah, I can see it. Here's an eye and an eye. There's a nose, a little mouth. Maybe. All right, let's look at the asteroid belt. Let's look at Ceres. We just looked at some cool asteroids, but let's go look at the actual asteroid belt. So let's zoom into the asteroid belt. We're going to fly a little bit. Here's an asteroid. This is Ceres, the asteroid. Ceres is much, much bigger. It's the biggest asteroid. Tells more about Triangulum. Triangulum is kind of a boring constellation. There's a lot of constellations that are named after, that are kind of like not historically interesting, including like there's Mensa, where a lot of insufferable people are, like Triangulum, Austral. This is the second Triangulum, but notice it's a triangle. Hi, Jones Dylan. I'm doing great. And you know what? For you, because you brought it up, you're the first person who's brought it up on this. I'll say, I'm doing great. You and me, Jones Dylan, you and me. We're going to start this flying through Ceres up. World 1-1. It's something I hate doing. So if we go and look right now, if we go back to so this is an asteroid belt, like a proper asteroid belt. And here's an asteroid on the asteroid belt, right? Ceres is cold, no atmosphere, very low gravity. It's not particularly, hospitable. It looks kind of like the moon because it doesn't have the atmosphere, so it doesn't, no little rocks crash into it. Just a kind of interesting little asteroid here. And the thing is when you think asteroid belt, you think, oh man, asteroid belt. It's like Star Wars. There should be asteroids all over the place. And that is not the case. Can I see any other asteroids right now? They are very far apart. The total mass of the asteroid belt is like maybe 3% the mass of the moon. So like an incredibly tiny amount of the mass of the moon. Nice to meet you too, Jones. These asteroids are leftover bits. Like if I do this, you can see Ceres, but we still haven't seen any other asteroids. Like I wonder if I can I wonder if I can look up and find asteroids like in a star browser. Can I do that? Can I do the search and look for, filter system, object parameter, not stars, object to search. Yeah, I don't think I can do that right now, but like, there's just not a lot. And if I like turn on our, so there, if we zoom, Ceres is red. This region right here has little rocks. Maybe most of them are the size of a house or boulders. Actually, most of them are very small, but the biggest ones are the size of a house or a boulder. And they're just so far apart that you really, if someone tells you like, oh, the odds of successfully navigating an asteroid field are 1, like you should say, no, they're pretty easy. You could just like fly through and not crash into anything. Not a worry. So after that, we got a planet most people really enjoy. I'm going to turn off my trails here, which is Jupiter. Jupiter is the largest planet. About 1,000 Earths could fit inside of Jupiter. You can see one of Jupiter's little moons here that we're going to fly by. I really love the moons of Jupiter because, like, most of them are little captured asteroids. Does this guy even have a name? Probably not. No, looks like it doesn't. Oh, Almathea. This is a dwarf moon. Almathea. Cold asteroid. Just a captured asteroid here. There's Almathea. Just looking like a potato because Jupiter's captured it. Jupiter is the first non-rocky surface object we've looked at. It's a gaseous giant. So, like, the surface is, like, entirely composed of gas. There's probably at the very core some sort of surface you could land on. I wonder what happens if I try to land on Jupiter right now. But mostly what you're seeing here is you're seeing gases in the atmosphere that are swirling around each other in the same way as I've said before. Like, if you take and put creamer and milk in coffee and stir it up, you get these little vortices and stuff. It's the Kelvin-Helmholtz instability. This is a giant vortice. This is a big storm called the Great Red Spot. But you can see there's all sorts of these little vortices over the surface. It's very, very pretty. Jupiter has a ring, but it's incredibly hard to see. But the most amazing thing about Jupiter is that Jupiter's just got moons aplenty. So if I go and I put back our chart here, and we look down at Jupiter, these are the brightest of Jupiter's moons, Amalthea, like Io, Europa, Ganymede, Callisto. But there's other ones here that they've got. So let's go look at Io. Whoop. Turn this off. We center on Io. And then we go there. Here we go. Here's Io. Io is incredibly volcanic. And you can see that they've simulated the volcanoes here. Io always looked to me like it had a pizza face. A yellow pizza face. And that's a lot of sulfur that's spewed up by these volcanoes, but you can see all this volcanic activity. And we can see sometimes from the Earth, like on the edges when like a volcano blows up and right on the edge, we can see the volcanic, what it spurts up into space. And so if we landed here, you can see on the surface of Io, which doesn't have any atmosphere, it's very, very low, 1 × 10⁻⁹ of an atmosphere, no real atmosphere, but mostly sulfur, silicon dioxide, or sulfur dioxide and sulfur oxide in the atmosphere. You can see what Jupiter would look like from the surface, which is pretty neat, right? And like, let's do this. Are you ready to do this? So now we're letting things rotate. And so this is over a long period of time as we speed up time. You can notice that there's other objects here that are kind of going around. These are the other moons. And if you go really fast, you can see them as they orbit around. And now we're going to have a solar eclipse from Jupiter. And we're back here. So the first person to notice all these things, these large, bright moons, was Galileo. So these are called the Galilean moons of Jupiter. So if we go back to the current time, and I set our normal time speed, we can look at another one. We can look at maybe Europa. I like Europa. Europa is, it says, cold, airless mini aquaria here. Europa is covered in ice, dirty ice. All you see here is dirty ice with these tracks on it. As the ice has water that kind of gets pushed up between these like essentially floating icebergs, very thick icebergs. And under the surface is actually salty water, right? Notice that Jupiter is not seen. Oh, there it is. Sometimes it's hard for me to find it. Notice we're a little farther away, so Jupiter doesn't appear as bright. But we think that there is a possibility that there's some sort of interesting life under the surface. And the reason that we call this a mini aquaria is because it has aquatic features under the surface. We also see spurts of water between these and water volcanoes, which is pretty interesting. You could do a whole bunch of work just looking at Jupiter's moons. There's a lot of interesting science. We're hopefully sending spacecraft to land on Europa and maybe burrow in and look and see what we can see, or orbit around Europa to do this. Jupiter and Saturn both, the next planet out, have tens and tens and tens of moons. And many that are still being, we keep discovering them is kind of how it is. But speaking of, let's move on to Saturn. So if I click on my solar system browser and click this and center, we're moving farther out. Ooh. Everyone loves Saturn. It's most people's favorite. Also, a lot of moons, quite a few moons. Saturn's pretty because it has these rings. And the rings are what happen when you have too many moons. And over time, those moons crash into each other and those spread out the material into big bands of little particles of rock. And so you can see here, if I look right in here, as we get closer and closer and closer, that this program simulates them as being bands, like slowly orbiting and rock and moving through. Little bits of rock, which is pretty incredible. Little bits of rock. If the Earth's moon were to break apart, well, it'd be very bad for us, but maybe over a long period of time, we'd get a ring like this as well. The rings, as you can see here, make beautiful shadows on the surface of Saturn, which is kind of interesting. And what I really like is if we click on one of the moons here, like Pandora, which you might be thinking, wait, isn't that from Avatar? And I'm saying, no, it's a planet. I don't think that's simulated in here. This is a dwarf moon, frigid asteroid, but I like it because it's right here on the other side of the rings. It's got a pretty big butt there. And if we land here and slowly let our orbit, we can see what it would look like to live on the surface of a moon of Saturn. And what's neat is that this moon is right on the edge of the rings, so they don't really get a good view of the rings, right? Some of the other moons get a better view, like Iapetus here, which is another frigid, airless microaquaria, gets a much better view of the rings, hopefully. I don't actually know. Wow, it's a little farther away, isn't it? We're getting closer, getting closer. Whew. Oh yeah, Iapetus. I think that on my undergrad final... Oh yeah, Iapetus is interesting because Iapetus has this ridge across the surface. Notice it's got like a ridge, like right here. I think I put a picture of Iapetus. Oh man, look at that. With Saturn right on the distance and all the other moons. If we turn on time now... you can see it's slowly rotating. All the other moons are rotating, but Iapetus rotates very slowly. There goes Saturn. Iapetus is just really, really chugging along slowly. So, let's get right up on here. Let's look at the rings. Here, this moon, right here. Let's try this guy. Dione. Another frigid airless microaquaria. But hopefully, you're seeing that many of the planets aren't super different. Yeah, also, I guess the thing is that most of the moons orbit along the same plane as all the moons must have, and so they over time, like, but here you can see they don't really see the rings. The rings are very, very, very thin. Anyway, the most important moon of Saturn is Titan. Titan has an atmosphere. Titan right now is coming to us inside of the constellation of Orion. Pretty cool. You can see Orion right here as we slowly get towards Titan. You can see the Orion Nebula, which we talked about last time. I've turned up the exposure compensation, but I can put it back to where it was. But notice, Titan has like a fuzzy atmosphere to it. Titan's different than the other planets that we were looking at in that it has an atmosphere. And that's interesting, because if we land on the surface, you can see that the atmosphere is 1.4 times the atmosphere of our planet. It's still negative 291 degrees, but it's a cold lacustrine subaquaria. And we think that there might be opportunities for life on this. The atmosphere is mostly carbon, hydrogen, and nitrogen, so there's not any oxygen. But besides the fact that it's incredibly, incredibly cold, it's still an interesting place that maybe there is some interesting early types of life there. But you can see through the atmosphere, the sun here appears, you know, like it's a hazy day in, like, you know, Los Angeles or something like that. But Titan is another planet we want to really go to, or another moon we want to go to and check to see if maybe there's strong evidence of life on it. Pretty cool. Chugging right along, we go to Uranus. So you can see, by the way, I haven't been saying it, but Jupiter here, Jupiter's orbital period is about 12 years. So it takes 12 years for Jupiter to go around the sun. And Saturn's orbital period is like, what, 22 years? 29 years, right? So some of you are 1 Jupiter year old. Some of you may be 1 Saturn year old, right? Uranus, though, hopefully no one, maybe someone watching is 1 Uranus year old. It's 84 years. Uranus just celebrated its, like, you know, recently 1 year of, I guess actually Neptune was it. But Uranus is, it takes 84 years to go around. So let's keep going to Uranus. Oh, there it is. Uranus is blue because it's got methane. And what's really cool about Uranus is it's also got rings. But Uranus is tipped on its side, man. It's tipped on its side. And those rings, kind of hard to see when you look at it this way. You can see the rings if I put the sun here, right? Those rings are also tipped on its side. So Uranus rotates not like any of the other planets. First off, it's weirdly kind of backwards, but it's also on its side. It has these rings that are on its side. And you can see here, if I do this, the moons also do this. Something knocked this planet over and all of its moons and its rings. I've asked astronomers who work on this why they think this is the case, and there's not been a really good explanation. But Uranus, all of its moons here, orbit in a plane with the rings that is tipped over. So the whole solar, like if you look at its orbit here, this is its orbital motion, right, along this red line. And notice it's got a weird tip to it. Why? How is that even possible? How did it do that? Strange, strange, strange. I like that Uranus is currently described up here as a frigid Neptune as opposed to a frigid Uranus because it's Uranus. Mostly just because we use Neptune as like a descriptor. It was discovered, as it says, with direct imaging. It was the first planet discovered that was not known by antiquity and by people seeing with your naked eye. It required a telescope to find it. And when they discovered it, they wanted to name it George's Star after King George, or Georgium Sidium. And instead they decided to name it Uranus. Like 8 or 9 years later, they discovered uranium, and they also named it after the same, after Uranus, because it was just in Uranus frenzy. It's another gas giant, couldn't land on the surface because of the thick gas. The blue is from methane, which is what makes farts smell. I'm going to show you, I'm going to actually pause all this stuff and set normal time speed and set it to current time. I want to look at one of the moons of Uranus. I want to look at Miranda. So let's look at Miranda. Miranda, one of the Sex and the City women. Miranda has the largest, like cliff in the solar system, and it'd be a thing where you could, because of the gravity on Miranda, you could just like jump off the cliff and then slowly fall. And so you can see Miranda here has a lot of these interesting surface features right here. But these things right here, the cliff is called the Verona Rupes. I don't know if I can find it exactly, but you can see, like, if you were to stand up on this and jump off, you had like a platform that was extended way out here. Like, this would be like, miles and miles of falling, slowly falling. Maybe if you had like some sort of suit. There's no real atmosphere on here, but the gravity is much less. You can see it's 0.008 gravity. And if I go land on the surface, boom. The gravity is still 0.008 of what the gravity is on the Earth. So you could jump pretty high, and you could fall the length of this, which I think would be really amazing to think about, like, cliff jumping off of Verona Rupes here, standing up here off the surface. So it says right now we are 21 miles off the surface of Miranda. So if we go off towards the cliff, really zoom in. It's starting to pull away. And then if you were to jump off, 21-mile fall. (15, 14, 13, 12) as we slowly landed. Much, much slower than this. Pretty neat, right, to think about? I think that's pretty cool. Especially because as you look up, you'd see Uranus floating above you, which is pretty incredible, right? Off this base jumping here. Miranda. Pretty awesome. And then, if we look back at our solar system chart, you can see that Uranus has a bunch of Bianca, Cressida, Desdemona, Juliet, Portia, Rosalind, Belinda, Puck, Miranda, Ariel. Do you recognize these names? Yes! They've named the moons after Shakespeare characters. Oberon, Titania, Umbriel, Ariel. Ariel's from The Tempest. Puck is from Midsummer Night's Dream. Juliet is from... I can't remember that one. Titania, or Oberon is also from Midsummer Night's Dream. You can see over here that Promethea, Pandorus, Janus, Epimetheus, Mimas, Enceladus, Tethys, Dione, Rhea. Like, these are other characters from Greek and Roman legend. But, like, the moons are often named after, things that, like, characters or gods and stuff. But let's go to Neptune now, which is referred to as a frigid Neptune. So let's go there. Flying off. Bam! Neptune also blew from the methane. Neptune has supersonic winds, incredibly fast-moving winds. You can also see here a great blue spot, which is a storm similar to the gas storms on Jupiter. Incredibly high winds. And as you can just barely see here, we can turn on our exposure settings. Can you see it right here? Neptune also has the bare, faint traces of a ring. Right here, you can see it. One of the rings. There's the ring. Faint ring traces. Not a very strong ring. Didn't have the same thing that happened where moons crashed into each other. Right? And if we go and look at one of the moons, let's see, I wanted to... I don't think I have a moon thing that I want to talk about here. I had one for, as I said, for Miranda, but, but it'd be kind of fun if we go to Larissa. It's weirdly egg-shaped because it's a frigid asteroid, very cold asteroid, right? But if you were to live on it, you'd be able to see a beautiful, beautiful Neptune off, constantly. So, let's keep moving outward because we're almost done with the hour. And if you have questions, you should please ask me. I want to talk about Pluto. So the thing is that Neptune is the last planet. Outside of that is a whole bunch of little rocks, kind of like the asteroid belt, but they're rocks that are much colder, and there's a lot more ices and stuff. And those rocks are known as the Kuiper Belt objects. And the largest Kuiper Belt objects are these four: Pluto, Haumea, Makemake, and Eris. Pluto is maybe the most famous one, because it's the one that was also... So to tell you how Neptune was discovered. Neptune was discovered mathematically. They looked out at the orbits of Uranus and said, you know what, Uranus looks like it requires another object that's pretty big out there in order for it to be moving in a specific object. So there should be an object like this big, like Neptune size. They didn't know Neptune at the time. That should be out there. So they mathematically predicted where it would be and then took a telescope and found it. Pretty cool. Pluto was discovered by looking out for maybe something else and just looking every single night to see if you could find an object out there that was moving from night to night. The high winds of Neptune are probably caused, I think, by the fact that you get solar heating. It's just a very tenuous gases, and any solar heating probably causes any atmospheric warmed by the sun, even if it is very cold out there, will cause, and also the rotation of the planet will also cause, you'll set up different gradients that will cause really supersonic winds. I think. I'm not a Neptune wind scientist. I'm not a solar system scientist, but it it also, the core will generate heat, internal heat, that will cause it, that heat needs to be given out some way, which will cause this difference in heat that generates winds. But that's a good question, Tiki Tech. So here's what I want to do actually. Here's something fun. So let's go back to the Earth really quickly. And from the Earth, let's look at Pluto. All right, so this is Pluto from the Earth, seen from the Earth. Now you can't really see it, but we can zoom in. You thought it was this. It is not this. Right here. We're still zooming in. Still can't see it. Still can't see it. Still zooming in. Really just zooming and zooming and zooming. There's Pluto. Right? So look at how much zoom you had to do just to see this, right? If it's like this, can you like pick out which one it is? Yes, you know it's the one in the very center here. But it takes a very, very powerful telescope. And notice that telescope is one, like, you know, that resolves all these objects here. Like, it's very, very difficult to find it. And so if we look at it here, we look at this right here, and we turn on time really fast. This is what was looked for, was an object that was traveling. So the next night, the next night, the next night, the next night, you're trying to look to see if you could find, you know, the object that was moving, which is pretty incredible. So let's return back to here. Let's return back to now. Let's go to Pluto. Quite a distance out there, way out there. Pluto is incredibly, incredibly cold. If we land on Pluto, you can see that it's negative 360 degrees Fahrenheit. And this is during the day. The sun is there. Look at how far away it is. If we go over, woo, really motoring, maybe too fast. To the nighttime side, negative 380 degrees Fahrenheit. So even on the daytime side, it's not much different because the sun doesn't really provide a lot of heat this far out. You know, we're a ways away. If we put on our solar system browser here, and look, you can see that the distance is 39 times farther than the Earth. 39 times farther than the Earth. We sent a spacecraft that went by there, you know, some number of years ago, and it took these really great pictures, which is what this program uses. And we see that there's, you know, ice and nitrogen ice, like, all over the surface here with some rusty color from iron. It's a pretty cool planet, or dwarf planet, and it also has big craters, just like we would expect because there's not much atmosphere, although it's rare that rocks crash into it. But you can see that some of the craters have been like some of the ice here has gone over the craters, which shows that there's current activity that is happened that changes the surface, which is pretty interesting. It has a couple moons. Here's Charon. Which doesn't nearly have the beautiful surface features, but it's still pretty interesting. And from the surface, you know, the sun here, pretty cold, pretty far away. I think I've done the wrong thing. If we rise up again and look down, we can see that we're pretty far out, but notice how far away Pluto and Charon are. And if I do this, if I turn on their orbits, you can see that their orbits actually like do a really interesting dance together. So there we go. That's what I want. There we go. So let's turn on our speed again. Notice that they kind of do this dance around each other, right? This weird wiggly dance. And this wiggly dance is because they are both pulling on each other as they spin around, right? So it's not like the Earth, which is pulled by the moon, but it's so tiny that it's not nearly as noticeable as this. These both are orbiting around a common, what we call a barycenter over time, right? So some specific point in space that like is moving, which is why I can't just put my mouse on it because it's moving around the sun. But there's other moons. You can see another moon right here, probably. I think this is Nix. Yeah, and there's Nix right here. Nix is much, much, much smaller. And it's a frigid asteroid. It's another object that kind of has an interesting shape here that was also probably captured from the Kuiper Belt out here, right? So it's now nearing the end of the hour. Those are the planets. And one of the dwarf planets is, if I really zoom out, you can see them all here. The light green ones, those are the orbits of the main planets, the 8 main planets. The 4 inner ones are way down there. These are the 4. 1, 2, 3, 4. This is the Earth right here, right? The 3rd planet out. That's the Earth. This is Ceres in the asteroid belt. Jupiter, Saturn, Uranus, Neptune. And then way out here, you get some other planets, which are the other dwarf planets, which have weirder orbits. And this is because there's a big band of a bunch of objects out here called the Kuiper Belt that are all that these originate in. Most of them are not shown in this orbital view. The 4 inner planets are rocky. The outer planets are gaseous, and then you get a bunch of the rocky Kuiper Belt objects. There's a lot of interesting stuff, and hopefully in the future we can talk more about some of the stuff. I've got friends who work on these things, and it'd be fun to have another person on as well to do this. But for right now, I want to finish up. This has been really great. If you have any questions, you should follow me on, oh, my shirt is glowing. You should follow me on Twitter at Kevin_Hainline, Hainline, or Instagram, which is just Kevin Hainline, no underscore. And just tune in a couple weeks as we'll talk more. I'm hoping to get up and talk about some galaxy stuff. I think it'd be fun to talk about extrasolar planets. This program simulates extrasolar planets, which is pretty interesting to do. Hopefully I wasn't entirely floated, like see-through the whole time. But if I was, that's kind of a neat aspect of this. But thank you guys so much, and have a nice rest of your night. Bye, everybody!